All right, welcome to this year's Raj Reddy Artificial Intelligence Lecture. This annual lecture is made possible by the group of friends and supporters of Raj in recognition of his contributions to the field. Some of them are in the room today, so we thank you for your support. It's my honor to welcome today today's speaker, Torsten Hoefler. Hoefler? Okay, I'm good. Torsten is a professor of computer science at ETH Zürich, a member of Academia Europa, and a fellow of the ACM IEEE on ELIS. He received the 2024 ACM Prize in computing, one of the highest honors in the field. His research interests revolve around the central topic of performance-centric system design and includes scalable networks, parallel programming, and performance modeling, and he will tell us all about it in a second. He has received many awards, and for this I need to take my piece of paper because it's going to take a while. Torsten won Best Paper Awards at the ACM IEEE Supercomputer Conference 7 times. Is that allowed?
Yes.
Okay.
I can tell you a story about it.
Yeah. Twice at the High Performance Parallel Distributed Computing Symposium, at the International Parallel and Distributed Processing Symposium, among other conferences. He's published hundreds of peer-reviewed scientific conference and journal articles. He's received the IEEE CS Sydney Fernbach Award, the ACM Gordon Bell Prize, the ISC Jack Dongora Award, the Lastis Prize of ETH Zürich, as well as the German Max Planck Humboldt Medal. We are very excited to have him with us today. Please join me in welcoming Torsten.
Thank you very much, Marshall. So it's great to be here, I have to say. Can I get my slides? But it's perfect. It's a real honor to be here. And it's so great to be here because I was able to meet Raj for the first time. I was also able to meet Guy for the first time. I watched many of his lectures as a young student, and I just learned that Gordon Bell was here. And this is going back to my roots of parallel computing in so many different ways, and also to my new roots of artificial intelligence, because Raj was contributing much to that field, if not most to that field, that actually forms the basis today of what I'm talking about. I'm a high-performance computing person. I started with parallel computing, and then about 2017, or 2016, I started to help Microsoft to build large-scale infrastructure. And then at the beginning it was quantum. And in 2017, one of my friends called me up and asked me, do you know what a transformer is? And I'm like, yeah, that's a substation, you know, that transforms electrical. And she's like, no. The AI transformer. And I'm like, I have no clue. And that's how I started in 2017. But of course, you all knew this much earlier, so I'm kind of one of those people who joined the field late. But then I was able to actually improve things that I'm going to talk about in a bit. And it was really an honor to talk to Raj this morning for a long time about all kinds of interesting things. And among those, I learned that he's been with CMU for actually 56 years now. Think about this. This is 10 years longer than I'm alive. So actually 11. That doesn't tell anything about your age, Raj. It's totally okay. So that deserves a round of applause for him. So, thank you very much for having me. And I want to start even earlier than 55 years ago. I actually want to start really at the beginning of humanity. This is going to be a very long talk. Right? So Stone Age we start, right? But no, jokes aside, we all know essentially how humans have developed. We took materials, we went from various materials to craft very simple devices. We then moved to a more advanced construction and manufacturing business. So from Roman technology, medieval technology, Renaissance to the Industrial Revolution. That changed the world as we know it today, to the world that we know today. And actually one of the major things that happened in the Industrial Revolution is that human physical strength stopped being relevant. That is a huge difference to before. Wars are fought with machines, which is very sad, but they are. And much of the construction is just orchestrated by our little weak brains in some sense. So I can operate a 10,000 or 100,000 ton ship, no problem, as a single human. I can operate a plane. We got together to build all of these things, but then we didn't stop there. We went to the atomic age, the space age, and then something interesting started. The digital revolution at about 1990. I mean, many of you still remember. Then we had the information age, and what most people believe today, we are in the data age. So we took the digital revolution to build computers, and then we wired them up to connect all of these machines globally to share the data as we do it today with the internet. Right? So many people would say we are in the data age today. Then one question I put there, you can think about this during the talk. I will not give you an answer, but this is an interesting question to ponder, actually. So now, I will claim in this talk that we are actually beyond the data age. We have exceeded the data age. We are entering, as humanity, what I would call the age of computation. And again, we're at a very central spot here at CMU, because I also learned that many of the parallel architectures are developed here and actually grew from here. And I just heard every single architecture gives you a factor of 10, so I'm waiting for the next one. So please give me another factor of 10. So why are we not in the data age anymore? I'm assuming, you usually ask this question, who knows this company? So it's kind of pointless at this point. So everybody knows this company. The funny thing about this company is that it's a unique company in the history of humanity. It's actually the fastest growing company ever recorded. It is the largest company today. It's not the largest company in terms of history, because that's the East Indian company. But it's the more valuable than all pharma companies combined, and it's at the 97th percentile of all national economies. So it's crazy, $4.5 trillion. But what does this company actually do? This company builds compute accelerators, has nothing to do with storage, nothing to do with data. They simply build processing engines. And so this point I want to drill in. It's not about much of the data anymore. We have used the data. We are now moving into the next era where we generate data. And you can see this if you believe Sam Altman. So more than a year ago, actually, OpenAI was generating 100 billion words per day. That is just 1,000 times less than the spoken words by all humans on the planet. Today, I would claim we're probably at the same level, but nobody publishes these numbers anymore for obvious reasons. So that's an interesting one. We also, even 2026, 23 people predicted that at 26 we would be running out of data. That's clear. People talk about synthetic data. I'll partially talk about that. Synthetic data could be better than real data. So, and then what comes shocking is, can we build an AI scientist? So can we actually replace much of the people, amend much of the people that we are doing today? And in my group, we've been driving this forward as parts of a project we call Graph of Thoughts, and I'll be talking about that in a little bit more detail in a minute. But at the end, the major message I want to deliver is that computation is really the new oil. You probably still remember about 10 years ago, it was data is the new oil, because many people built on data systems and bought big databases, like Google acquiring YouTube, for example, a big source of data. But today, everybody builds big data centers, and that's the new oil. The nice thing is that we now even have oil in Switzerland, where I'm from. So it's a very small country, has basically no natural resources, but we have the fastest supercomputer in Europe. So we bet on this. We actually built the largest AI machine together with Jensen when AI was not a thing back in 2017. But now mega data center providers build larger ones. Why did we do this? Well, we train very large language models that are actually open language models. So this Apertus model is the largest, most capable, fully open language model, which means fully transparent data. You can download the whole training data set for this thing as well. It's not as good as the other models, but it is fully open. Okay, so now, how did we get to this? And how we got to this is an interesting story that I want to share with you, which is basically starting from my opening joke in about 2017 when people asked me what a transformer is and I didn't know. A transformer is this structure. It's a computational structure. It's actually a very, very simple computational structure. It's actually so simple that you can explain it to your grandma. It's really, really, really simple. Each of these boxes is some form of very simple computation. So it's either a matrix multiplication, very simple normalization, some simple statistics. So, and then you have multiple of these boxes. So it's about 12, 13 functions that you have to call in this thing. But at the end, what they do, these transformers, the original ones, they take some form of input language. They take some form of other output or input language. So for example, here in English, here in German. And then they generate the most likely word for the next translation. This is why they're called transformers. So they transform, it's kind of a silly name, I think, but this is why they're called like this. And now it generates the most likely next word. So it's an autoregressive process that generates more and more words. So very simple. And what turns out, this is super simple computation, as I mentioned, 95+% matrix multiplication. So that's what actually drove the field forward, because in high-performance computing, driven by Gordon Bell, actually, we designed computers to be really good at matrix multiplication, because that's very relevant for many scientific problems. This whole field was riding on those computers, basically. writing them forward. GPUs started in high-performance computing. They only later went into the AI space. And then, of course, we have, there's much more to be said about this, encodings and tokenization and high-dimensional vector spaces, so I could talk about that as well. But I don't want to do this in this talk. There is more to say. But at the end, all of that structure is extremely simple. I cannot emphasize this enough. This is very, very simple. You can write that from scratch, literally within 2 or 3 days, this thing, like from scratch, from nothing. Okay, wonderful. So we have a very simple structure that we use to derive all of the AI models today. This is underlying every single large language model, this structure. What happened then, this was 2017, a long time ago. 2018, people looked at this, well, can we actually use this structure to develop some form of language understanding? Can we show that the model somehow understands what a specific word means? And this is where it came to bidirectional transformers. So BERT is bidirectional encoder representation for transformers. It's bidirectional. We remove one word, and we have the model predict the missing word. And if it could predict the missing word well, the thesis was that it would kind of understand. It's hard to define what understanding means, actually, really. It's kind of an ill-defined concept. But understand the semantics of that word it's adding into the thing. And that was actually successful. But then the company who designed this, Google, they put it on the shelf, pretty much. Then some other company came, which many of you now know, it's probably one of the most valuable companies on the planet. Not quite as NVIDIA, but very valuable. They came and they developed this GPT, generative pre-trained transformer. So basically they took half of this thing, just the generating part, to generate language out of nowhere. Like this had 2 pieces. This was generating language from an input language to an output language, but you could now just generate language out of nowhere. So based on the prefix, you generate the most likely word. Right? That's how it works. Really, really simple. And it turns out that just by learning the statistical distribution of language, interesting stuff happened. That's literally how it worked. Interesting stuff happened. Then later they scaled this up. Right? This is scaling laws, and this made it really interesting. So basically, you would give this language model some kind of text, and then would give you the output text. So we all know this. I don't want to go into detail. It's kind of general knowledge today. But what was very interesting, what they looked at what is the compute? What happens if I invest more compute into this? So the validation loss would go down. What is the validation loss? The validation loss is basically the quality of the model. So the lower, the better. It's a loss function. Right? The quality for predicting the most likely word out of the language distribution. You can never achieve 0 here, because if I'm telling you a car can, the next possible words is not a single word. Drive, park, they're equally likely. Maybe drive is more likely than park, actually. But you can never hit 0 in this benchmark, but you can go down. It's still debated what the actual entropy of the human language is. So that's an unknown quantity. But you can go down, and you see the more compute you invest, the more you go down. That is the other thing you see, that's a linear scale, kind of, and that's a log scale. So this year, petaflop per second days, if you think about what that is bad. Because petaflop per second is the largest machine that we had in about 2012 in the United States. It was a machine I helped construct, the Blue Water supercomputer, $500 million investment by the NSF. One of the biggest, actually the biggest investment in compute that the National Science Foundation ever made. That was 1 sustained petaflop per second, that machine, $500 million, about 10 years ago, maybe 11, 12 years ago. And now you see that is 100 times that, and that is 1,000 times that. Right? So we made quite some progress. You could also make a similar argument for the number of tokens, the number of words the model sees. So of course that compute is just ingesting additional words. Great. And what happened then is they published this paper on scaling laws, which is absolutely great. Because the scaling law paper literally says this: the optimal model size grows smoothly with the loss target and compute budget. That was in about 2019, and then everybody was like, okay, let's scale this up and hope we get to artificial intelligence in some form. That was literally the scaling race started at that time. That was a kind of an outline paper. Like, look, let's try that. Let's scale up. And the whole industry aligned. So Microsoft, I was part of Microsoft. I still am part of Microsoft. At the time, we pledged $1 billion into OpenAI, essentially. We built the architecture. They ran the thing, and everything else is history. Like ChatGPT came out of that, right? So that was the original pledge. There was even a comic about the supercomputer that we built. But then Google, an advertisement company, a search engine, builds supercomputers now suddenly, the largest computers on the planet. Facebook, an online network builds supercomputers. Oh my God, what is going on? Tesla, a car company, builds supercomputers. Like in the good old days, Gordon Bell was alone with his 15 friends building supercomputers. Nobody really cared. Today, every major company invests in large-scale computing. That is a completely crazy business, actually. If you look at the number of GPUs sold, 2023, you see that Microsoft and Meta, private companies, were the major customers for these supercomputers. It used to be the US government. It used to be the Department of Energy building the big machines. No, not anymore. Microsoft, we just published a machine the week before last, or maybe last week, the Fairwater machine, which is 10 times bigger than the fastest publicly listed machine on the list of the fastest machines. Of course, this machine is not described in great detail because it's an industry, but that's an interesting one. And then 2024, you see interesting, there's suddenly all kinds of Chinese companies here, right? ByteDance and Tencent, and they're now number 2. Okay. So then we talk about a huge investment. Of course, Trump had to say larger numbers. So it's a $500 billion investment, so $500 billion to just throw at compute, essentially. The Stargate initiative is literally building a large computer. And it's interesting because this machine actually begins to exist in Adelaide, Texas. They built a gigantic machine. Okay, so what do we do with this? Well, actually what we do is still the same thing as I mentioned at the very beginning. We take a lot of text off the internet, we remove a word, we run it through this very simple computational structure. It's just really big. Then we get kind of the probability distribution of the possible next words out of this. So you can see what, and of course we know which word we removed, because we removed it in the first place. And what we do then is we train this thing, right? So we all know how this works, right? We adjust the weights with a very, very simple scheme. It's stochastic gradient descent. It's the simplest possible gradient scheme you can imagine. Second order methods are more complicated. They don't really work. But what we do is we run this on a very large model with a lot of tokens. And actually, today we have trained on the whole internet multiple times. The model is so large that actually, and this is the last publicly known model. The private models are significantly bigger, I can tell you, but I can't give you the exact numbers. So it's 1 terabyte of data to just store the model. So you can't really store it in your memory of your laptop, right? You get very large, and it takes weeks to train on the most powerful computers that we have today. Like, so that's a problem. So now what we did in 2020 was to actually look at this computational structure. Did I mention it was very simple? So we looked at this, we analyzed it, because this number was kind of scary. They said it costed $12 million to train the thing. But actually it did cost $12 million. It was so expensive that they had a bug. They couldn't fix it because they couldn't retrain the thing. Right? So actually, if you read the original GPT-3 paper, in the appendix, they will tell you, oh, we had this bug, well, too bad. So that was it. Then you look at the computational structure. What happens in this model? So 99.8% of the floating point operations of this model are literally tensor contractions. That's matrix multiplication. That's literally matrix multiplication. And then you have these 2 other things that are 0.2%. But matrix multiplication is so heavily optimized because the whole world optimized for matrix multiplication for multiple decades thanks to the top 500 list. People like Jack Dongarra got the Turing Award for it like 2 years ago, I think. So highly optimized, great. So which means the model is really, really fast. No, it's not, unfortunately. Because these 0.2%, they cause nearly 40% of my runtime. So what did that mean? So 0.2% of the operations I'm doing are 40% of my runtime. So where is my time? Makes no sense, right? It does make sense because you need to move the operands around on chip. It was all a data movement problem, which you don't count as operations because you only count the multiplications and additions. So what we did is we looked at the data flow graph of this thing and we achieved a 30% speed up at the end of this model. Did I mention that's $12 million to train? So that is $3.6 million saving. Today, people say that these models are worth about $1 billion. So that was achieved with a data flow graph. So we basically looked at the whole thing in terms of data flow. We looked at different data layouts. I don't want to make this too detailed and too boring. I want to give you the overview. By the way, for each of those slides, basically, there's a full talk for one of my students online on YouTube, which you can watch for 30 to 60 minutes explaining all the details in case you want to dive deeper. But I just give the TED Talk style overview here. So we have different fusion strategies for different kernels. We have a large graph where you look at the right combination of data layout and fusions for these kernels to make it very fast. At the end, we do an automatic search and we get these speedups. So this is all in production today. Like these, we get a 30% speed up end to end, which is great because reducing the cost, actually, we need more. Like 30% is great, but 30% doesn't cut it. So let's look at what happened. We had this era of model size scaling, which is literally people were looking at larger and larger and larger models, and this is still going on, but it's kind of tapering down. And then ChatGPT came out. ChatGPT was only 3 years ago. To me, it seems like it has been 10 years ago, but it was actually only 3 years ago. And what happened there, they took this model and they turned it into a very nice assistant, into a helpful conversational partner. That's great. Now, overnight, they basically created a business that had millions of customers. It's completely crazy. Well, it's a very useful tool, and they gave it away for free. So, of course, everybody signs up for it. And then the challenge with this is, now, if you need to serve that model, did I mention that it's very, very, very large? Which means it's computationally extremely expensive to serve it. Right? So now if you're at the other end, and I was at the other end at the time, you have a problem. The other problem is that actually now competition shows up. So open models appeared. So now this is the closed model of OpenAI, but open models with Llama, they basically said the best way to compete in this market is to not compete directly with OpenAI, but the best way to compete is to form an open source community where everybody competes now with OpenAI. Right? So that's the trick. Like if you make your thing open source, then you can actually create a much larger movement. So that's also an interesting one. So, but now what do you do in order to to serve these models where you reduce the cost, either to smaller models, you make the models computationally more efficient, or you reduce the hardware costs. These are the three ways you can reduce costs for these models. Okay? And what we did then is we went into the era of data scaling. What does that mean? We stopped scaling the models, but we scaled the data. We ran more high-quality data through the models. Many people call this the chinchilla effect because the first model doing this was called Chinchilla at Google. So now we need even more compute because we run more data through the now slightly smaller or not much bigger model, let's put it this way. So that's great for people like me because I'm a deliverer of compute power, so that's great. But now it was pretty obvious that the performance optimization of these machines really determines the future. At this point, that was around 2023, everybody understood that the more compute power you have available to train your model, the better you will be, the faster you will be reaching the potential goal of whatever is general intelligence. I'll be talking about that in a minute. So that's now nice. But now you need a scientific approach to do this if you want to go fast. Now the next couple of slides I'm going to show you how to increase or improve the cost by about a factor of 1,000. This is what we did in my research group, but also at Microsoft with many collaborators. Like there are tens of people involved in this whole thing. So most of credit goes to them. But I already mentioned that moving the data is most expensive, right? So now what we were originally assuming is kind of the traditional HPC view, where you optimize your application without changing the application itself. So it's kind of the, I would call it the Gordon Bell view as well. So you take an established application, you make it faster on a specific machine, but you're not allowed to touch the application. In machine learning, it's different. You're actually allowed to touch the application because at the end, it's only approximating a probabilistic distribution that's a natural distribution from a language. We always sample from that distribution. And then now I can change the representation of that distribution. So why don't we just shrink the data? Like that was the first attempt, or the first approach, which is very, very successful. Because now you could look at this. My brain has very limited precision. Why the heck do we train in 32 bits floating point? Why is every of those 500 billion parameters stored in 32 bits? Makes not much sense. Do you need that whole range? Do you need 2 to the 32 different states? And the answer is no. So now the question is, does anybody know how many different states a neuron in a human brain can differentiate? Anybody has a guess?
2 states.
Well, 2 is a little bit less. It's a little bit low. That's only, no, it's a little bit more. Sorry? 7 plus or minus 2. Well, that's getting better. But actually, you can read this in this eLife journal. It's about 24. So which means, on average, across many neurons, which means my brain operates at 4.6 bit. Right, log of 24. Of course, yours runs at least 5 bits, so that's fine. But I may be running at 4.2 bit, but who knows? And this is now interesting. So how can the brains get away to run with that low precision? And we run with 32 bits in machine learning. So that, I understand if you're a biologist, you're probably upset now at me because this is not. There are many flawed points of that argument, but it's interesting. How did biology end up with the 24? So now we have 540 billion parameters. So that's actually 1 terabyte, as I mentioned. And now it turns out, if we just take these parameters and round them, just round to the nearest representable number in the smaller bit width, it's perfectly fine until 5 bits. If I round to 4 bits, my model quality will be gone. If I round to 5 bits, it's great. So that's just empirically observed for these models. Nobody knows why. That's great. Actually, it also turns out that there was a recent study that says that the model has about 4.6 bits, really. It's also an interesting one. The meta study. You can read what's the real information content of LLMs. So what we then did is we basically looked at the mathematical background of this. So biological systems are great, but we looked at the mathematical background, and I want to give you just the intuition because it's more complicated than I can explain here in a couple of minutes. So let's look at a single parameter model, x1, one parameter, right? So that's the two-dimensional space because we have a loss function and a one-dimensional function. Let's make it look like this. So what we typically, this is my loss curve. So what we typically do in SGD, we start at a random position. We initialize our weights randomly, and then we go down to the nearest local minima. Right? That's SGD, and then you get stuck in this thing. Right? So perfect. So now what we can do is we can take this function and we can expand it as a Taylor expansion. Right? We can say, well, it has a first order term. That's the gradient. If you're in a local minimum, the gradient is hopefully 0. Otherwise, your model is not, or close to 0. Otherwise, your model is not converged, right? So if you have trained it to the end, the gradient is close to 0. It turns out that the higher order terms are actually also close to 0. So the third order and higher. And that's actually true for quadratic loss function. It's definitely 0. But there are more complicated, like cross-entropy loss functions. But even those cross-entropy loss functions, in practice, empirically, they have very low third order. So what matters is the second order. Like the thing in the middle. And the second order you can imagine as the curvature of the arrow. Right? It's a very simple curvature. And now if you look at this, now if you have 2 parameters, right? And now I want to round, so we will go from 1 to 2, but now imagine this in a 540 billion dimensional space. Like that's hard to imagine for most humans, and I have no clue what that means. I can look at 2, I can look at 3, I can maybe look at 4, but then it stops. But let's look at this 2-dimensional space. So if we now had to round some number to the nearest representable number here, which would you round, x1 or x2? Where is the arrow bigger? Do you have a guess?
X1.
So you would round x1 because the arrow is smaller in rounding x1. Exactly, because if you make a little step here, it's flatter. And this is exactly what you want to do, parameter by parameter by parameter, 540 billion times, which is what you can't do. But at the end, what we did is we came up with this GPTQ scheme, and it was mostly led by Dan Alistar. And we phrase this as a mathematical problem. We solve this. We solve a lot of tricks because, of course, in a 540 billion dimensional space, it's problematic because you would need to create the Hessian for this. You would need to invert the Hessian. The Hessian of this is a matrix of size 540 billion times 540 billion. That is not practical. Like, there's no computer on this planet where I can even store this matrix. Long story short, at the end, we went down to 3 bits. So we could do 3 bits without significant loss, like less than 1% loss. So that's great. Actually, it turns out that the method we invented, we just published that a couple of weeks ago, is equivalent to Babai's nearest plane algorithm, in case you're a mathematician. So we invented that from scratch, and it turns out later, somebody invented that about 50 years ago, but we didn't know. So that's reassuring that we invented the same thing. So we get a factor of 10x, 32 bits to 3 bits. That's the first factor of 10. Okay, but now how do we go further? So, and again, I would want to go back to brain inspired somehow. So what also turns out, actually Raj came up with this idea this morning, so also independently, somehow our brains are not densely connected. And somehow the question is, why are we using dense matrix multiplications for all of this? Makes no sense whatsoever. It turns out for technical reasons, I could go into much more detail why we do dense matrix multiplication. It's actually tricky. This field is very tricky. But what you can do is, what you can see as an intuition is that not all features are always relevant. For example, in this text here, you can read this text. Even though it's missing about a third of the letters, but not all the letters are relevant for us to read this text and understand this text. So it actually happens that we can remove many of the parameters and many of the weights in the model, and the model, actually up to 95%, and the model still has exactly the same quality. Because most of those are very small. So that's interesting. If we can remove 95% of the weights, well, we are saving a factor 20 approximately in computation. Right? That's another at least 10x. Actually, it turns out this field is so complicated. I wrote a paper myself as a first author on this field after reading 500 papers that are related to this. This is the longest ever paper that appeared in the Journal of Machine Learning Research, JMLR, which is one of the top journals. The editor probably still hates me. So that we also extended with a scheme that's called SPQR. So now the question is, if I quantize the model and I sparsify the model, does this work against each other? Because both remove bits from the model. And the answer is no. Very surprisingly, I was surprised. I didn't know this. Actually, turns out the first author is now at CMU. So he's an assistant professor here. So we collaborated with Tim. Great. So that's 100x. So we get a 10x times a 10x, that's 100x. So, however, if you now sparsify all of that stuff, data movement becomes even more critical because we have less compute and more data movement now suddenly. So now we need to build very, very heavy networks. And I'm an engineer, I build stuff. So what did we do? Well, we looked at the way we connect computers, because the network itself of a supercomputer is the major component. This is where the computer lives or breaks. I very often say it's the cardiovascular system. Many people say it's the heart, but no, it's not just the heart. It's the full cardiovascular connection system of the supercomputer. So if you make a mistake there, it's bad. What people typically do is they build global fat trees, a topology that was popularized also co-invented by Charles Lyserson, the advisor of Guy. And so that's a great topology. Unfortunately, it's very expensive. You cannot build that at the bandwidth required. So what people did at Google, for example, they built a two-dimensional torus where you only connect with your neighbors. If you only connect with your neighbors, you have very limited bandwidth. That's a very bad cut, this network. So what we did, we developed a trade-off between the two topologies, which takes global connectivity for fat trees, connecting multiple locally connected pieces. So it's a Hamming graph of a mesh, and I don't want to go into too much details. It basically combines all of the features of the two, allows us to find a technology trade-off between these two topologies. You adjust the size of these local pieces, and then you get about 10 to 15 times cheaper. That's another 10x, right, for the system. And there is a very long talk that I'm giving on this whole thing in case you care about this. I just didn't want to spend too much time. Okay, wonderful. So at the end, we developed scientific principles to optimize these AI training and also partially inference workloads. I didn't talk about I/O, but I talked about compute and communication, the networking pieces. And if you care about the whole thing, there's another YouTube video, 1 hour long, where you can just listen to this, how to optimize these systems. So now we got 1000x. But what do we do now? Well, the timeline, we were only at 2023, now it's 2025, so we move on. What actually happened? So now how do we move forward from LLMs? And I try to avoid the term AGI. I call this AHI. I think AGI is ill-defined because we don't know what general intelligence actually means. Nobody so far could define general intelligence for me. I believe that humans are not generally intelligent because for some task, my calculator is simply much better than I am. Like multiplying large numbers. I'm not very good at this. My calculator is so much better. So I call it artificial human intelligence, which really means that you can measure it compared to humans. Like, can you beat the best chess player? Like, that's a very clear task. Can you beat the best Go player and things like this? So now it turns out that Ilya, one of the founders of OpenAI, he said, well, pre-training as we know it will unquestionably end because we have essentially exhausted the internet at this point. That was more than a year ago. It's true. We have essentially exhausted the internet. But while doing so, we have generated a model or many models of a capability that is already superhuman in some dimension. Because this model or these models are better in answering questions about general knowledge than any of us in this room is, for sure. Even all of us combined, we would not be able to beat a GPT-5 style model at this point. Okay? Just general questions. And this is quite astonishing. And actually here you see statistics. These are different exam tests. And this is the percentiles of humans aligned from the worst human to the best human. So this line is the average human, the 50th percentile. Whenever a bar is above this line, the AI model is better than the average human in taking these text-based, like I'm talking to you now, asking a question, test. You see that the AI model, and that's a couple of years ago, that's only GPT-4. Newer numbers were not published. So GPT-4 is already better than most of the humans in most of the tests. Right? And today we are way further than this. But what we can do, what these things cannot do, they could not reason at the time. So now how do we get these models to reason? To have a multi-step conversation, a multi-step thinking process. We call this thinking, but it's quite hard to define thinking in details if you're a mathematician. But basically the way we use these models was what I call basic input-output. So you query the model, you get an answer. what is the capital of France? And then you get back Paris and something like this. Very simple question-answer things, which they basically, all of those tests were very simple question-answer pairs, many multiple choice actually. But then if you ask them, and the model could do this because it literally used the most likely next word prediction to do this. Now if I ask the model to sort some numbers for a sufficiently long sequence, it has not seen that sequence in its training data. So it cannot go into its database and retrieve that the capital of France is Paris, because it doesn't know the sequence. So it would need to retrieve a sorting algorithm and then execute that sorting algorithm. But it couldn't do this because its only capability is to predict the next likely word. So that was a fundamental flaw in these models. And now it turned out that was a very surprising result, that, and many of you know this, that a chain of thought. So who knows about chain of thought? Yeah, exactly, nearly everybody. And that was a surprising result where you basically, in the original one, you gave the model an example. You told it, hey, to sort some other sequence of numbers, you do this. And then please sort this sequence of numbers. So that was very surprising to me. Like, wow, okay. So if you give the thing, it's like a little child. You explain to a child how to do things and suddenly it develops the capability to repeat it. And then it got even better because there was this wonderful paper that's just called Let's Proceed Step by Step. It was basically telling the model, please don't just blabber an output along, please proceed step by step. So give me the intermediate steps, because the model, of course, knows this example. This example is in the training data of the model because somebody has explained to somebody on the internet how to do sorting, right? It's just you needed to tell the model to actually look it up. Right? That was astonishing. That increased the performance on these benchmarks by about 10%, which was a huge number at the time. It was not perfect. It was not perfect at all. And then people extended this whole stuff. We have multiple chain of thoughts. We had tree of thoughts, where we can now take a thought and split it into multiple sub-thoughts. And then what we developed in my group is what's called graph of thoughts, where you basically take two thoughts and combine them again. In a tree, you cannot combine things. In a graph, you can combine things again. This is how we mathematicians work. In order to reason, we have theorem 1, theorem 2, and then theorem 4 uses the result of theorem 1 and theorem 2 to prove theorem 4, for example. Like, so this is a very natural thing. So this is great. This happened. But now, how do we get to those thoughts? And this is a major question. So I want to make a small detour to AlphaGo. So there's a fellow human called Lee Sedol. He's the 18 times world champion, one of the highest ranked Go players ever alive. And back in 2016, something very interesting happened. So he was challenged by a machine, by Google, and he lost the matches. He lost so badly that he quit his job. Like, his only job was to be the best Go player. And he said, I'm not playing anymore competitively because this machine is too good. So it beat him really badly. How does that work? So it actually worked back in 2016. There was not a whole lot of compute available, actually. So how does that work? Well, we model the Go board as a state. Like, so some model as a state. What you do then is you ask a so-called policy function. This is reinforcement learning now, most of you know. You ask a policy function, how do I get to the next, what is a good next move? And of course you sample. You ask it m possible next moves. What you do then is you ask another function, it's called a value function. How likely is it from that state that I'm winning? And the trick was, and then you go with this, with the most likely state, you expand it again, you assess the likelihood again, you realize you need to backtrack, and you do this over and over again. So it's a very simple algorithm. The trick here was that they used a deep neural network to represent the policy function, and a deep neural network to represent the value function. Very simple deep neural networks at the time. So they actually ran it multiple iterations. So, and this is essentially the story of AlphaGo and AlphaZero. What is the difference between AlphaGo and AlphaZero? AlphaGo was a model that they trained with this strategy based on human oversight data, based on human existing games. AlphaZero was a model that they trained with zero knowledge. AlphaZero actually outperformed AlphaGo much faster than AlphaGo, which means the model got distracted by the human knowledge, which means without the human ever teaching it, it would have been better. Think about that. Right? So that's an interesting one. Right? So it actually became superhuman without any human advice, in some sense. So now if you think about this, how can we apply this to deep learning or to generative AI? Well, we have a thought, and then we ask a policy function, what is the next good step in order to solve this problem? You can ask an LLM to do this. So for example, the LLM may say numbers are blue. Well, that's kind of stupid. Or you can say, look up quicksort. That's not so simple and not so silly. So now we could again assess the quality of the next thought with a value function. right? And then we do the same thing. We now look up quicksort. Okay, now we can ask again, basically having this chain, what is happening? And then you could say pick pivot if you know about how quicksort works. It's the first step, and so on. And then you run this basically on a human language-driven approach. Now the only problem is that your policy function is a deep neural network, and your value function is also a deep neural network. Did I mention that they're extremely expensive? That is now the major challenge. We can run this already. We will be able to solve extremely hard problems with this approach. Because it's literally, we have the best human knowledge database, and we have a way to put it together with the best superhuman strategy. Running this in a loop will be extremely powerful if we had the compute power, which we don't, to do this, right? So that's nice. I can go into more technical details, but I just want to give you the high-level picture, because now what's happening is that this is what happened. This was the DeepSeek moment. Some of you remember. Stock value of many companies dropped by multiple tens of billions. Okay. So now this is implemented in practice. We can look at this. Actually, if you ask Gemini today, sort these numbers, it gives you exactly a reasoning thing. Like you can see a blah, 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 choose a sorting algorithm, apply sorting, blah, blah, blah. You also see that it takes forever, right? And it gives you all these detailed steps. So this is an extremely expensive query, right? So this is number one. What you then realize is actually, can this do math? So there was a very interesting benchmark that came out last year, Frontier Math Benchmark, because people got upset that many people said that, or press actually said publicly, math is solved because the GSM-8K dataset got solved. So there was many newspaper articles. So all the top mathematicians got together and said, no, we make a real math benchmark that AI will not solve, the Frontier Math Benchmark. And indeed, at the time, none of those AI models actually had any reasonable success rate. So that was smaller than 5% solved. So that's basically random guessing. If you guess something, you'll get there. And so even Terence Tao, one of the Fields medalists, said this is going to be extremely hard in November 2024. Well, the reasoning models came out in December 24, and they got 25% right away. So that was a shock for everybody. These reasoning models are pretty good. They also got really, really good in the thing that's called the ARC challenge. That's something that's designed for humans, where basically the performance until 2024, the end of 2024, was 0. AI models couldn't do it. It's really, really a very, very tough task. I don't want to go into details. But immediately it jumped to nearly 100% right after. Just last week, a couple of days ago, actually 3 days, I think, they announced a model, a tiny model, that rules all of these models in the reasoning challenge. So we make a lot of progress in this field. It's very, very, very fast. If you think you're a good coder, think again. If you think you're in your PhD, you're safe. No, think again. This is all kinds of interesting stuff happening in this field. So all of these benchmarks are jaded in one way or another, by the way, but they show a general trend. We shouldn't take them too serious, but they show a trend. But now what does this mean? What does these models combine, these reasoning models? They take superhuman strategy and superhuman knowledge. I just established both, right? Superhuman knowledge, that's the standard model that looks up facts. We have that. Superhuman strategy is the Go player. We beat the best human in pretty much any defined game. Now, if we put those two ingredients together, we must get to artificial human intelligence. Because these are the two human features we have. So that's an interesting one, and this is why I believe we are going into the era of reasoning scaling right now. Reasoning models are there. We need to scale them up. But did I mention that they're extremely expensive? Okay, so that's now the problem. How do we do this? By the way, this is an ARC challenge, and we don't have enough time to do it. But you should play ARC at home. I play it sometimes if I want to fall asleep. It's a very nice game. This is one that the AI couldn't solve. And if I had 5 more minutes, I would let you do it, and you would be able to solve it. All of us would be able to solve it. So we are not done yet. We need to improve these these reasoning models quite a bit. So now we wrote a paper on this. In case you care about more details, you can read that paper or watch another talk that's also on YouTube. So I'm getting towards the end of this timeline, the era of reasoning scaling. But how do we now moving ahead? So first of all, I want to give you one other argument why these 3 eras exist. So the argument is the cost per 1 million token in the public OpenAI API. You can see in 21, it actually increased from 21 to 23 because the model size increased. Like we had the era of data scaling, right? And then it went down because the model size decreased, right? That's now interesting. Higher training costs though, but the inference cost went down. And now with the reasoning models, it's completely crazy because there's a task that costs $5,000, like a single task, because you can run this reinforcement loop until the end of time. So that's an interesting one. But now what does this mean? So we basically need cheaper compute at this point. What's driving human progress, at this point, we are compute limited as humanity, in some sense. We have an algorithm to move forward, but we are compute limited. So how are we contributing to this? Well, I'm helping Microsoft. I built this, helped them to build this Maya architecture. NVIDIA is building Blackwell. Other people are building other architectures. So principles are the data types I mentioned, sparsity, spatial optimization. So these are the underlying principles to build next generation AI hardware. I would say we can get a factor of 10 to 100 on top of what we already have. But then we are running out of steam. Because at some point we cannot quantize more than 0. I mean, 0 bits doesn't help anybody. 1 bit is too small. So we have a problem there. Right? We are running out of steam. The other one is we need cheaper systems. And that is actually even more important. And this turns out that at least at the Microsoft pain point, the system, the cardiovascular supply, the network itself, got extremely expensive of those systems. Because there was essentially only one vendor that would deliver those. And I mentioned that vendor before. Most valuable company on the planet because of that monopoly, essentially. Right? Because there was only one. But now we need to reduce the cost of these systems. At the end, we're all cost constrained. Energy is also a cost factor. Like, how much do we want to invest in terms of energy and capital investment? So what does that mean? I want to focus the last couple of minutes on the network piece because I talked about the architectures before. So what happens is actually very interesting. Every data center will be a supercomputer. In the good old days, we were making a difference between the very powerful supercomputer networks and the normal data center networking architecture. This is changing because there will be, if you want to be an AI player as a data center, you have to have a strong network, period. So that's opening a market that is of unseen dimensions in that area. So I wrote this paper earlier that hyperscale data centers and high-performance computing networks will converge. We measured all of this. Turns out that what we have today, data center Ethernet, is not a good, it's called Rocky. It's not a great idea. So there are many issues that I could go through, but I don't want to go through. But if you care about this, you could just read that paper. And then we founded what's called the Ultra Ethernet Consortium. Because it turns out that in the commercial world, it's all Ethernet. And actually in the general world, networking is pretty much equal to Ethernet. Like if you open your wireless device, you're talking Ethernet frames. If you're playing with your phone right now, you're talking Ethernet frames to the access point. Everything is Ethernet, even wireless is Ethernet. Also, like the year before last year, the Turing Award went to one of the co-inventors of Ethernet because it's so important. So Ethernet was not capable to execute AI workloads very efficiently because it was not designed for high performance, it was designed for high reliability, which is a very different goal than high performance. So we basically got together, and I represented Microsoft in the founding companies, and we founded this consortium, and we can talk about more details. It's a nice consortium, actually. We sit in this room, we discuss. I'm not on this picture, by the way, because I'm the chair, and I'm taking the picture. And this is my wonderful co-chair, Karen Schramm. So she's doing all the work. I just take the pictures. And that's how we work. It's an industry consortium, and everybody can join. It's open. We have lots and lots of member companies. But I want to quickly give you an overview of what it is. If you're familiar with the ISO stack, this will be very quick. So we have the application layer, where all of these AI applications sit on top of it. Right? So this is the programming layer to the network. At the very bottom, we have the Ethernet physical layer. It's literally, this is this plug here. That's an Ethernet physical layer plug. So everybody has it, every laptop. No, actually the newer laptops don't have this anymore, but every kind of desktop has this. So exactly same layer. So then there is a data link layer in Ethernet, which is the way you establish a connection at the other end of this cable that we don't change, and that we speak Ethernet frames over this thing. So you can look at the number of bytes here for each of these fields. If you're a networking person, this will be very familiar. And then we have some extensions there, but also it doesn't matter. But we are using the exact same protocol as the internet because we need to be compatible with the high-performance data center with the existing infrastructure. This is the difference to networks like InfiniBand. They don't run over IP. They're not compatible with the data center environment. They're not compatible with the internet. Again, this thing is fully compatible with today's internet because, as I mentioned, today's internet largely runs over Ethernet, largely routed by TCP/IP. Which is a layer on top of Ethernet. And then you can go into details, and then the major difference in this thing is actually the transport layer. So the transport layer is the layer that reliably delivers messages from source to destination. And I could go into much more detail, but I don't want to because I don't have time. There are lots of interesting features that we introduce in Ultra Ethernet. So there's actually a paper on how to do this. And one of the major features I wanted to introduce is how you route through an existing network. So this is now a computer network. These are computers, these little gray things, and these little green things are switches. Each of those switches has input ports and output ports, right? That's very, very simple. And we apply a very simple routing technique that is actually quite cool. This is why I want to share it with you. The technique is very simple. You take a field in the packet that you call entropy value, and then you apply a fixed hash function. So you always have to go to the top, right? If you go upwards, and then at some point you go down in this network. But let's only look at the up path. You apply a fixed hash function to determine which output port you choose for an incoming. So you don't have a fixed route that has one output port predetermined, but based on a value in the packet itself, you apply this hash and you select an output port. Now the source of the packet can change that value. And now what is guaranteed if the hash function is deterministic, that the path will always be the same if the value is the same, but the path will likely be different if I choose a different value. So now if I'm sending with entropy value A, I may take this path from the source to destination. If I'm sending with entropy value B, I may take another path through the network. It's a very interesting mathematical problem to figure out how these paths come into play and how to do routing in this. You can also do this from C to D, again, two different values, you lead along two different paths, very likely. So that's just something I wanted to share because it's a very cool idea. It's very different from how we've done it in high performance computing, but it actually scales better. Okay, if you care about these details, there's a full paper on this online, again, that you can look at, and you can find all the nitty-gritty details of how Ultra Ethernet works. So with that, I want to get to the end, and I want to summarize again. There's 1,000 times improvement that we've achieved in the past. There's the whole history, which I cut into 3 pieces in this age of computation. The era of model size scaling, the era of data scaling, and now we are in the era of reasoning scaling. So we have to scale up these reasoning models. Then I believe that this reasoning scaling may actually lead us to AHI. It's pretty likely if we can get the compute supply to the model. It's very inefficient right now. If you look at many of these specific outputs of these models, they're very silly. The reasoning paths go into la-la land and then talk random things, but it's getting there. And then a big part of the infrastructure is actually the network of these supercomputers. And I also covered that. And then there are many, many more smaller things that I want to just leave on the slide. And now I'm open for questions. I still have 11 seconds left, but we can use those. Thank you.
Thank you so much. Questions? Yeah.
First of all, thank you so much for your wonderful speech. And I want to ask a question about that slide when you mentioned that we have super thinking and super knowledge. Mm-hmm. So we have this like superhuman AI.
Yeah.
But I want to ask, for humans, we remember things.
Yeah.
Like instead of like we have knowledge like pre-train, but we learn and inference at the same time.
Yeah.
I wonder for this step, is there any ongoing thing or look forward things about like if AI can remember things for so long and can train and inference at the same time?
In fact, that's a very good question. So people emulate this today. So we don't really understand how humans actually store information and how humans learn information. So for example, it's not clear if we are already primed to learn a language. Right, if it's encoded in our genes somehow, right? So there's a lot of theory on this, or a lot of suspicion. So in the models, the base model is never updated. It's not updated on the fly. But what you do is you can apply so-called adapters, like low-rank adapters. You may know LoRa, to update models on the fly. What you can also do, and what most people do, is you can do in-context learning. So you can simply remember. Like when you say, I learned something new, I can feed this as my prompt into the model over and over again. Because today, Gemini says publicly, they have 1 million token context window. 1 million tokens is a very long conversation. If it's a very, very long conversation. If at some point I share, for example, I have my chatbot relationship, I share that my birthday is the 21st of March, and then on the 21st of March, you ask the question, what should I do today? A language model is actually likely to tell you, a good language model is, hey, you should celebrate your birthday because you said it maybe a year ago, maybe 100,000 tokens ago, 100,000 words ago, but it would still find it in its local context, which also has the benefit that you don't have to share that context with other people. right? So other people using the model. There are these two major ways. So one is training adapters, and the other one is using in-context learning. In-context learning, you can actually use another scheme that's called RAG, retrieval augmented generation, that you store this data in some file, and then you retrieve it based on demand. But in some sense, that's just a context extension because you can RAG larger databases, like gazillions of tokens now. And this is the way you can emulate learning. I know your question was probably different. I gave you an engineering solution to a very deep question, if we should update the models during inference, right? That nobody does, and I think that has something to it. But it has all these technical problems. For example, if you update, if I, in the conversation with you, update my GPT-5 model, which is gigantic in size, then you don't want that model to be used by me because it has your information in it. So we need some kind of smaller update. We don't want to update a gazillion weights. And most of that knowledge is actually shared. Because most of that knowledge in the model that's stored is how to speak, how to all these world facts and whatnot. So the stuff that's personalized to your conversation is actually very, very small. And that you want to keep separate. It's an engineering solution. Does that make sense?
Yeah.
Okay, cool. Thank you.
Yes.
Yeah, I think this was a super interesting talk. So I want to put on that thread of how you walked us very nicely through this transition, ending up with compute as being the new oil.
Yeah.
Are we at this point where instead of compute as being the new oil, we are at the point of saying power is the new oil? Because you see all of these new announcements from OpenAI, and they're talking about gigawatts of transactions, right? They're not talking about dollars, they're talking about gigawatt transactions. And kind of related to that, as you look at these different supercomputers that everyone is building now, where does energy go, especially as you start to put more networking into the picture? Like, what's the mix, and where are the hardest problems you start thinking about from that?
Those are great questions. I mean, let me answer them piece by piece. So the first one, you said, people are saying they're limited by energy. And that's a surprising statement, actually, because you may think you're limited by capital, by money. But if you're OpenAI, you can basically just create money. And we're seeing this right now, that they're creating money in loops. I mean, some of you are smiling. Exactly. This is the new economy. You say, oh, I'm investing 10% in AMD, and then AMD stock grows by 25%, and AMD gives you 10% for free, and then, oh, but we've grown by 25%, so they make a 15% gain. So I mean, you can basically, in today's economy, if you're a big player in AI, you can just say, give me money, and money will flow. No, I'm serious. This is actually what's happening. And there are pretty arbitrary amounts that are flowing. And so the real limitation you have is actually energy, because even if you have infinite money, deploying energy is not easy, especially not in regulated countries like the United States or Europe. There are other places where this is much easier. But building a serious power plant, which gives you gigawatts, takes 30 years of planning. Right, so you can hardly do this. And this is why everybody says we are energy limited, which is very true, because it's just an engineering constraint. You cannot build power plants faster than 2-3 years. And 2-3 years is ages in this field, right? So that's your answer. It's mostly an economic/engineering answer. So that makes perfect sense. And now I forgot the second part of the...
Where is the...
where does the energy go?
What's the distribution of the power in these...
Yes, I'm sorry. For me, it's...
And where is it going? And where do you think it's going?
Yes. I'm sorry for forgetting the question. I mean, for me, it's already midnight now, so I have a little excuse. So where does the power go? That's a great question. Actually, most of the power today goes into memory on these machines. So that's about 50%, so that's a little bit more than 50%. Then the compute part is actually not that much if you exclude the data movement. In fact, most of your energy, like the vast amount of energy, probably 90% or so, is in some form related to data movement. Much of that data movement happens on chip. So it looks to you like it's actually compute energy, but it's actually energy to move data on the chip. We don't have very good data on this. There's some older, for the modern chips, for the older ones, we can easily tell it's 90+%. Also, on-chip memories require a whole lot of memory, so it's all a whole lot of power. So it's all about really data movement, but at various levels. The network is just another device for moving data, which is, if you wanted to separate it out, network takes about 20% of the overall system, and then the remaining 30% go into your chips. So it's unfortunately relatively flat. So if you make the chips to 0, you don't gain that much. If you make the network to 0, you don't gain that much. If you turn the the memory to 0, you may be gaining a factor of 2. But it's also not much. Right? So that's an unfortunate fact. There is no single big bottleneck. It's well distributed.
We have time for one more.
Oh no.
Hi, thank you for the great talk. We had lunch earlier today. You briefly touched on this. You said you were looking to three-dimensional architectures for data centers. And that, in the previous question, made me wonder to what extent we are hitting thermodynamic limits on computation. And there's some theoretical work on things like reversible computing.
Absolutely.
That's going to be coming in the near term, and does it have any implications for the design of topologies?
Oh, it's a great question. There's actually the fundamental limit is the Landauer limit. I don't know who's familiar with the Landauer limit. Probably nobody. There are some people. So that's actually the amount of energy you need to flip a bit from 0 to 1 or from 1 to 0. That's to generate 1 bit of entropy. That's very, very small, but that's your fundamental physical limit. And we're still about 1 million times, was it? Maybe 100,000 times away from that limit. Right? So reversible computing basically goes beyond the Landauer limit because it never actually flips a bit, it just redistributes bits. Right? So reversible computing breaks the Landauer limit, but we're so far away from it right now that I personally believe reversible computing doesn't make a difference today. Right? Also, quantum computing, you can make a similar argument. So it doesn't make a difference today, but it could in the future. So currently, our main optimization goals are, in fact, the data flow optimizations that are giving you most bang for the buck for your brain investment into this thing. And are we hitting fundamental limits? Yes. We are actually hitting fundamental limits of electrical movement on chip and beyond chip, so we move to optics. Right? So much of the data center infrastructure is already optical, because it has to be. But optics are also expensive because you need to convert now bits into photons, and that you lose energy in that process. But now if you go a very long distance, it pays off because you don't have the resistance, like photons are not affected by resistance. So now it's only a matter of cost in terms of latency, how long does it travel? But this is still why you want to build special topologies that are not that wide, because your latency is also critical for the overall computation. So it's a more complex multi-dimensional optimization problem, but you're right, there are fundamental limits. And we are not hitting them yet. But we can still take one question.
Yeah, I said it was the last question, but let's keep over my chain also. Yeah. So you'll have the last word. You'll have the last word, okay?
So thanks very much for our thought-provoking talk. I'd like to end things by putting you on the spot.
Oh my God. No, thank you not.
Sorry about that. It's too late now.
What we're looking at here is a chasing of resource. More and more energy, more and more oil actually burned.
Yes.
Generated.
Yes.
I can't get away from the fact that my brain operates on 20 watts.
20 watts, yes, exactly.
And I'm doing tremendous three-dimensional scene recognition here, but I don't believe I'm using CNNs for it.
No.
And so the question is there something fundamentally wrong with the neural network model? If we just did things better, we wouldn't need it.
And I can put you on the spot. The answer is obviously yes. Right? I mean, there's something wrong about it. But the problem that nobody really understands is how do we achieve this performance, this accuracy with a better architecture? Because we don't know. Right now, it's super brute force. I mean, this is a gigantic even the dense training is a total disaster. We have to train the model dense, and I can explain why. Because SGD sucks, because the learning algorithm is bad. The learning algorithm is really bad, actually. However, it works. And we have not found a better one. We know it's bad. We have not found a better one. So what do? It's a gigantic business, $1 trillion business. So we are willing to invest hundreds of millions of dollars in terms of energy and CO2 and oil and I don't know what into just pushing that business forward. We may not be ready to do so yet. We may discover a technology that's 100 times more efficient next week, but still that doesn't stop industry from moving. Right? So it's just a very human argument in some sense. So we as academics, we understand, but you can still use the very inefficient resource. And at some point, actually, in terms of efficiency, there's one argument to be made for language models. If I make you, I want to put you on the spot. If I make me create a piece of art or write a book or write a poem, I will generate more CO2 in that process, in that time, that as my human time, than a good AI model does to generate the same text, the same image, the same output. So actually, that is something to think about. The training, we don't know. But for inference, AI models are actually more efficient than human beings to generate most of their tasks, to program, because they operate with a very small CO2 footprint. They operate with it. So that is an interesting one, but I want to close with that.
Well, you left us with a few simple questions or challenges. Thank you so much.
Thanks, sir.
Thank you, everybody. Torsten is going to stay for a few minutes if you want to.